to see those on there, especially in this case. There's not resonance isn't happening here. So in this case, these are called isomers. These two molecules have the same molecular formula. You count 2 carbons, you count 6 hydrogens, and 1 oxygen, but it's a different arrangement of the atoms. These don't resonate between each other. These are 2 different molecules with 2 different sets of properties, different chemical properties and different physical properties. This one's an alcohol, and I think this is called an ether. The fact that it has an oxygen between the 2 carbons makes it something called an ether. So just by moving those carbon and oxygens, it makes them actually different molecules, even though they have the same formula. And this happens a lot with these carbon-based compounds because there's a lot of possibilities for whatever else is there. Here we can see on this slide the names of them. We've got ethanol and dimethyl ether. The molecular formula is the same formula. And then, Jeremiah, you mentioned something about like having that condensed formula. Sometimes there's a hint in the formula about how you're trying to like show that you wanted to emphasize. The first one has the O and the H kind of separately out on the side, and the other one has the oxygen in between. So when you see that, that's called a condensed formula. It's a way of representing that. That different the different arrangement of the atoms in 3D space gives these very different properties. And we'll start talking about the 3D shapes a little bit more tomorrow. Now, sometimes when you have different possibilities for arrangement, you have a special kind of isomer. All right, and this special kind of isomer is called a stereoisomer. And on your chart, on the bottom, I guess it's the 3rd row down, so on the back of your handout, it says stereoisomers in the 3rd row. And that's showing us this thing called stereoisomers. Stereoisomers are isomers that can occur when you have double bonds across, especially carbon, and then the carbons have different elements bonded to them. So double bonds are kind of different than single bonds in that double bonds aren't able to twist and rotate around. So the first one we're looking at there, the one on the left, is called the cis isomer. So I made this model. I'll pass these around. Green typically represents chlorine when we're dealing with models like this. Black is carbon, like coal, I think that's black, and then white is usually hydrogen. So this represents a cis isomer. So that means I've got the double bond, and then the chlorines are on the same sides of the carbon. In this case, they're both on the left side, but you can move it around. They could both be on the right side, or they could both be on the bottom, depending on how you're holding it. But the 2 chlorines are on the same side of those carbons across their double bond. And because it's a double bond, I can't twist them. They're always going to be stuck there. All right? Now this one has the same exact chemical formula and even the same connectivity because it's still, 2 carbons are double bonded. Each one has a chlorine on its own and each one has a hydrogen on its own. But that double bond is there. So this one's called the trans isomer. The trans isomer occurs when the 2, whatever the other element is, whether it's chlorine or bromine or something other than carbon and hydrogen are the easiest ones to look at there. So in this case, we're looking at green ones, which I use chlorine, but your sheet has bromine. They're across the double bond from each other. And that is going to represent the trans isomer. I can't twist these, so one will never become the other. Now, if I tried to do the same thing and it was a single bond molecule, the reason you never have stereoisomers when it's a single bond is because single bonds can rotate. So at first I might look at this one and say, oh, that looks like if you just had to guess, would you call this a cis or a trans isomer? Cis, because good. You can see the 2 chlorines are on the same side of the carbon across their bond there. But the thing is, single bonds, and it's true with the models, which is kind of cool, it's the same thing with the molecule itself. Single bonds can rotate. So now you would think, oh, it's the trans isomer after all. But it's neither one, because there's not a double bond there. It was never cis, it was never trans, it was always just the same molecule. So when you have single bonds, don't worry about cis or trans isomers. Turns out it's really crazy. Triple bonds also can rotate, but double bonds are the only ones that are locked into place. So to have a cis or a trans stereoisomer, you have to have a double bond, and then you have to have some kind of interesting element or part of the molecule other than just hydrogen that is different on one side or another. If they're both on the same side of the double bond, it's called the cis, same side. If they're across from each other, it's called the trans isomer. Yeah.
So that one also has got an additional element.
Yeah, good. Another bond. Yeah.
So what would that also prove that it's neither one of those?
It wouldn't have to, because you could have. Let me think about that for a minute. I guess it would. I guess they're one and the same. It's got the extra bond there. I was thinking I could just put a blue atom here and a blue atom there, like for a nitrogen or something, and it could still rotate and become the same thing. But sometimes something else happens with those that we don't study in this class. There's another kind of isomer called an enantiomer that might happen. If there were a third atom on one side, that might change something, but I have to think about that. It's a really good question. It's not going to affect cis and trans isomers, but it would affect another kind of special isomer called an enantiomer. Drawing this one on a flat piece of paper, again, I can make it look like a cis and a trans isomer, but I know that doesn't happen with single bonds. So if I say these two molecules, are they isomers? All right, these two molecules we're looking at here, I might say, are they isomers? And it turns out, no, they're the same compound. It's just rotated. This chlorine rotated up to the top. Now it's up at the top because the single bond is able to rotate. But as soon as I put a double bond in there, and this is what James was mentioning, the fact that I have to take out an atom to include that double bond to fit it in there. Now with the double bond, this molecule actually still is the same molecule there. I just moved it up there to the top. Move this. There we go. Drawing it this way, this molecule on the left will never become the molecule on the right, unless a bond breaks. If a bond breaks, I guess it could. But these two would be examples of stereoisomers, just listed a different way. These are up and down, these are left and right. So this is my trans isomer, and this is my cis isomer, where they're on the same side. The double bond cannot rotate. The cis and the trans isomer, one place that they're kind of interesting is with saturated fats and unsaturated fats. On the top you've got saturated fats, and on the bottom you've got a couple of unsaturated fats. As soon as you have a double bond between the carbons, it makes the fat what we call unsaturated. So fats are these long carbon chains. The top one represents a trans isomer because the long carbon chain, one's kind of on the lower left side of that double bond, and the other one's on the upper right side of that double bond. So that's our trans isomer. Have you ever heard of trans fats? We talk about trans fats as being very unhealthy. So it's called a trans fat because there's a double bond in there, and it's a trans isomer of the unsaturated fat. Cis fats are the other ones that are thought to be healthier for unsaturated fats. With cis isomers, you've got a double bond, and look, the carbon chain's on the lower side, and the other carbon chain's kind of on the same lower side of that double bond. So when they talk about cis fats and trans fats, they're talking about stereoisomers of the unsaturated fats.
Why is one healthier?
I think it's because their ability to kind of, the fats can pack together. If they're in those straight lines, they can pack together and form like really hard fats that can make your arteries hard. But when you have a kink in the chain, because of that cis isomer, did you notice it had like an angle to it? Having a kink in the chain keeps those fats a little bit farther apart, so they're not able to form those really hard surfaces. So it allows more flexibility for your arteries and such, I think is why. This kind of summarizes what we were dealing with here. Your job on the assignment is going to be to look at two different compounds side by side, or two different structures, and decide, are they actually different compounds because they have totally different formulas? Well, you'll know that by counting the atoms. Look at the first example. It's got 2 carbons, 4 hydrogens, and 2 chlorines. All right, the molecule next to it up there, it's got 2 carbons, 4 hydrogens, but now it's got a chlorine and a fluorine. So they have different formulas. They're different compounds completely. Totally different formulas, totally different compounds. All the others are going to have the same formula in some way or another, and you have to decide whether they're isomers or not. The first one, we call them constitutional isomers, or if somebody just says isomer, they're referring to just constitutional isomers. It's the same formula, but a different connectivity of the atoms. So they just rearrange the building blocks and put them in a different order. And you can see the first example in the second row there. It's got the oxygen connected to the middle carbon. This one connects the oxygen to the carbon over here on the end. So those are regular old isomers called constitutional isomers. When you have a double bond, you want to watch out for stereoisomers. It doesn't guarantee it's a stereoisomer, but when you have a double bond, you might want to look to see if you have a cis and a trans version. They've got the same formula. They've even basically got the same connectivity. It's just across the double bond, they've got a different spatial arrangement. The 2 bromines are on the same side of that carbon-carbon double bond, and here the bromines are on the opposite sides of those carbon-carbon double bonds, so that's the trans isomer there. So if it's not on your paper already, you might want to go ahead and label this one is cis, C-I-S, and this one is trans. Trans means across, because you're going to have to label those when you see the cis and the trans isomer, the stereoisomers. I want you to be able to tell me which one's cis and which one's trans. All right, and then finally, you got to watch out for kind of, I'll call them maybe trick questions almost. Sometimes they'll try to draw them in a way that makes them look like isomers, because they have the same formula, they have the same connectivity. You still have a carbon to a carbon. When you see H3, that just means there's 3 hydrogens single bonded to it. Kind of like that would be CH3. It's kind of a shortcut to show that. So H3C is the same as CH3. All right, and then a carbon's got a double bond to an oxygen, and then it's bonded to a hydrogen. All they did is they just took the one molecule and they flipped it around, and you're seeing it from the other direction, but it's the same molecule that's just kind of been rotated around, like looking at the back side of a sheet of paper. It's the same compound, same molecule. So it might look like an isomer at first, but it's really the same molecule, just kind of flipped around. All right, so that kind of ends where I'm going to be talking to you about this stuff. I want you to have some time to practice with a couple of things. I might recommend that you actually start on the second page of this. It's where you're going to identify. I've drawn a bunch of structures. You have to tell me whether they're regular isomers, which are constitutional isomers, stereoisomers, or the same compound, or if they have a totally different formula altogether. So you'll list that while you look at those structures. Then, the front page of this reviews Lewis structures and formal charge. So actually the first question you could have done after yesterday's lesson, Lewis structures and formal charge. And then it's got a little bit of stuff about ozone, not ozone necessarily, just ozone. It's got a little bit of stuff about resonance structures as well on the first page of this. Anybody have any questions? Yeah.
Tomorrow.
Yeah, this will be due tomorrow. But just like before, it's more spread out than you would expect, okay? Just because it's got a staple in it. I don't think it'll take too long. Like the whole second page, I've drawn the structures, and you have to tell me whether they're isomers or not. I'm drawing structures, so it's probably the same.